de Ciencias Nucleares, y en esta ocasión vamos a escuchar al doctor Sarira Sahu. Él es investigador del Departamento de Física de Altas Energías, y pues agradecemos que estén aquí presentes porque es un coloquio importante para el doctor Sahu y por supuesto para nosotros, que muchas veces intentamos que nuestros coloquios de divulgación involucren a muchos de nuestros investigadores. Entonces esta es una buena oportunidad para que se haga un esfuerzo de divulgación por parte de nuestros investigadores, sobre todo pues los que están del lado más teórico. Agradecemos mucho, doctor Sahu, por este ofrecimiento. Les voy a presentar al doctor Sahu. Realizó su doctorado en 1995 y posteriormente otro postdoc en Physical Research Laboratory en Ahmedabad, India, de 1996 al 97. Fue investigador postdoctoral en el Institute for Plasma Research en Gandhinagar en 1998. En febrero de 1999 llegó al ICN como investigador postdoctoral. Actualmente es investigador titular B y SNI 2. Hasta el momento ha publicado 56 artículos, con otros 2 más aceptados en revistas internacionales. Cuenta con alrededor de 600 citas y actualmente trabaja en física de neutrinos, rayos gamma de altas energías y teoría de campos a temperatura finita. Entonces, pues, doctor, bienvenido y muchas gracias. Adelante.
Hola, buenas tardes y muchas gracias por sus palabras. Ok, voy a hablar en inglés, pero cualquier persona puedes preguntar en español, no hay problema. Y cualquier tiempo puedes preguntar, no tiene que esperar hasta último momento. Ok, so I'm going to talk about something very astrophysical, or you can tell cosmological scenarios, that is called Blazar, which I am going to explain about that one. Blazar, a bakery for very high energy gamma rays and neutrinos, because this is something very interesting from the point of view that we don't have a machine to produce extremely high energy cosmic rays or particles. So only way to do this, detect these particles indirectly, to depend on the nature, okay? So we have to find sources where it is produced, and then from there we can detect these high energy particles, for example, gamma rays, neutrinos, high energy cosmic rays. So that is what my topic is. Okay, so my talk is basically framed in this way. I will first talk about what is a Blazar, why it is so important, and why we should study this one. Then extragalactic background light. This is something very important to detect extremely high energy or high energy gamma rays, because this is something which will obstruct this high energy gamma rays to reach to the detector on Earth. Then I will talk about detection of very high energy gamma rays, because that is the one which so far we are detecting with many high energy gamma ray detectors all over the world. And we have one in Mexico, that is the Hawk detector also. I will talk about that one a little bit. And the neutrino astronomy. neutrino astronomy is related to this high energy gamma rays, because if you don't produce high energy gamma rays, then probably you are not going to produce neutrino. Or you can tell that if you are producing neutrinos, you must produce high energy gamma rays. So these are things which are related. So I will talk about that one, and then I will summarize my talk later on. Now what is a blazar? Well, probably you might be knowing that blazar is a subclass of active galactic nuclei. Then now question comes, what is active galactic nuclei? Okay, so let's go. Active galactic nuclei is probably recently you might have seen this. They did an experiment where they, for the first time, they captured the light, low energy light, from a black hole, and they showed that. They showed the figure how the event horizon of black hole looks like, which I will show in the next slides. So that is something. A supermassive black hole is believed to sit at the center of a system where this matter is falling into this one. This is called the accretion disk. So this matter is falling into this black hole, and this black hole is supermassive in the sense that it is something like 10 to the power 8 times to 10 to the power 9 times the mass of the sun. So it is a the huge systems, and the matter is falling into this one. When the matter is falling into this one, because of the conservation of angular momentum, there are two jets coming out opposite to each other, and these are the jets which are coming. So this is a general structure, or this is, you can tell that this is a general structure of active galactic nuclei. The system looks like this, and particles are coming in this one. Then you go, okay, so this is a active galactic nuclei, but there are something called the unification scheme of AGN, which is subdivided into blazars, radio galaxies, and some other things. So that is basically what you see is that depending on where we are, suppose this is the jet, whether we are here, wherever we are, depending on that, we will see different aspects of different type of emission or different energy range particles from this one, and according to that, it is subdivided into different groups. So basically, because of this matter accreting into the black hole or going into the black hole, so this emits, these jets, which emits electromagnetic waves starting from very low energy up to the extremely high energy. So this is basically you can tell that it emits all the spectrums, okay? Now, so classification of active galactic nuclei, you see that, so active galactic nuclei, few percent of all galaxies, then they are radio quiet, radio loud, then this is divided into blazar, this is the one which I am going to talk about. Then, apart from that, this object, which is blazar, is basically the one when you are, when you are somewhere else within this cone, if you are somewhere else sitting here, then anything goes here, any change, even in terms of minutes of half an hour or 1 hour, 1 day, 1 week, 1 month. So any variation in flux can be directly seen by the observer, and they will see really the boosting because of the relativistic beaming effect. So because of that one, this object is called blazar when you are within this cone, okay, within this cone, very small angle in this jet axis, okay. So, so this blazar, around less than 5% of all the AGNs are blazar, and this is something interesting from the point of view that recently, well, not recently, within 10 years, many experiments have seen these type of objects which are responsible for extremely high energy gamma rays emission, first thing. Then some of the objects they had seen that they are related to neutrinos. Then also from flat spectrum radio quasars, few years ago, Pierre Observatory told that they have seen a high energy cosmic rays event above 57 times 10 to the power 18 electron volt energy from Centaurus A, which is the closest object and which is in this flat spectrum radio quasars group. So these are this is the objects, or blazars are the objects which are very important from the point of view of studying for high energy gamma rays, high energy neutrinos, as well as high energy cosmic rays. And from this, there is this subclass called HBL, the high energy BL-like objects or high energy blazars. This is something very important from the point of view that now more than 50 or 60 objects, all are HBLs, are being observed, which are emitting high energy gamma rays in the range few TeVs to around 20 to 30 TeVs. Okay, so far we have seen, and these objects, they quite often they have flarings in the sense that suddenly there will be eruption either in the low energy limit or high energy limit, but low energy limit I am not going to talk about. In the high energy limit or extremely high energy limit, suddenly they will see the flux will go up order of magnitude within few minutes, within 25 minutes or so. But they don't understand why this goes on. Okay, so now if you see how their spectrum looks like, so this is called the FSRQ, this type of object. This is LBL, which is this one. This is IBL, this one. This is HBL, and this is a new class of object they call extreme HBL. You can see from here that all of them have two peaks. One is the synchrotron peak, so-called, another is the inverse Compton peak, but this is not well established. I mean, there are still some debate going on that whether it is really an inverse Compton peak or something more than that. But this is well established. This is a synchrotron peak. Normally what happens is that in the jet, maybe I can, okay, in this jet, when the particles are going, mostly, let's say charged particle, electrons, when these electrons are going forward, and there is a magnetic field associated with this one, so these particles, these electrons will emit synchrotron photons, maybe it is there, okay, here, I think. So this is, you see, when you are within this cone, this is called blazar. If you are little bit off axis, this is called quasars, and if you are something like almost perpendicular to this is called radio galaxies. So these are basically different, viewing the same object from different angles. Now, these, well, I showed you there are two peaks. The first peak is coming because the electrons in the magnetic field, when they are going, they will emit synchrotron radiations. So that is the one which gives you the first peak. This peak will give. Then the second peak is believed that this, because these electrons are having power law, they are not thermal, they are power law, so low energy one will give you the synchrotron peak, and the high energy electrons, when they are propagating, they will kick these photons out, okay? So they will kick these photons out, and this photon will be boosted in energy, and they will give the second peak. So that is the inverse Compton peak, okay. Now, so this, whatever you saw the spectrum, they are non-thermal spectra, they are not normal Boltzmann distribution type. And radio variability across the entire electromagnetic spectrum, you will see the variation from the low energy to extremely high energy, high relativistic beaming, because you are within this cone, so you can see it is really beamed. Then boosting of the emitted power, shortening of the time scale, because these are the systems where particles are moving with the ultra relativistic speed, very close to the velocity of light. Okay? Then why do you study these objects? Okay? The first thing is that we don't know how the equation this, how the matter is falling into the black hole, and these jets are taking energy away. So basically extraction, energy extraction mechanism from the central supermassive black hole. So astrophysicists, they study this one. Physical properties of the astrophysical jets. So these are the jets, and they are having particles and photons, all very highly relativistic. So they will study the physical properties of these jets, because these jets can go up to parsecs, kiloparsecs. They will go simply just like that, okay? So they will study that one. Then acceleration of charged particle in the jet, because so far we know that these type of objects are responsible for high energy gamma rays or very high energy gamma rays, very high energy cosmic rays, and very high energy neutrinos. So one has to know how the particles are being accelerated, because you don't produce here these extremely high energy particles. These particles, when they are produced, maybe they are comparatively low energy, but on the way they will pick up energy because of the different mechanisms. And if by chance they will exit from these systems, then they will come as ultra high energy cosmic rays. If they cannot come, if they interact with the background particles here, then they will produce neutrinos and gamma rays. So that is the one has to study. And there is another important thing, is that constraint on the extragalactic background light. So this type of observation of very high energy gamma rays, particularly gamma rays, no other things, is very crucial to understand the extragalactic background light. Maybe next one is my, okay, so this is the one, this is the first peak and the second peak. As I told you, the electron, when it is in the magnetic field, it is emitting these photons. This is called the synchrotron peak, so this is the one. Then this is the power law of the electron. So electron in this higher energy end, they will boost these photons to this one. And you see, in this case, both these peaks, most electron is taking part, and electrons being left on, this is called the leptonic model. Okay? So this is the inverse component. Electron is coming, low energy photon, it will kick out, and then this will be higher energy. So this is the leptonic model. Now what happens? Okay, so this is in the this peak comes near infrared optical low energy peak, and this one is coming in the giga electron volt range. Now something, so probably you know, there is a 11-year cycles in the sun, when during these 11-year cycles, sometimes there will be flaring from the sun, intense flaring like this one, magnetic field will increase and all these things. So this can have disturbance on electromagnetic system on Earth. Now imagine that in these objects, imagine the highest flaring, whatever is taking the on sun, is multiplied by maybe few billion times. Okay, so that is the type of flaring it happens in these objects. That can last for a few minutes, that can last for one day, that can last for 1 week, or that can last for months also. So nobody knows why it is happening, but we know that it is happening, and from the many objects, many high energy blazars, they have seen that this is taking place. So it can go, for example, there are objects they have seen, 25 minutes it has gone 1 order of magnitude higher flux, and next 25 minutes it has come down, let's say around 30-40% of that one. So then it was varying like this. So this intense eruption, increase in flux in short interval of time, mostly in blazars, high energy blazars, tells that these are the things which one should really study and understand, because this will give us really the indication of the high energy gamma rays, high energy neutrinos, high energy cosmic rays, so that we can see with the current state of Earth Like for example, we have the Blazar, we have the telescope array, we have the IceCube, then we have high energy gamma rays detector like MAGIC, Hawk. So these, they can see this object through different probes. For example, Blazar can observe high energy cosmic rays, IceCube can observe high energy neutrinos, Hawk can observe high energy gamma rays from the same direction during the same time period, so that they will confirm that these are really the objects which are responsible for this. Okay? Now, normally what happens that because these two peaks are there, that every AGN will give you, irrespective of what they are, classification, so they will give this one. But they have seen that in some of these HBL, high energy blazars, suddenly they will see these third peaks or maybe somewhere else here. So this is mostly around few hundred GeVs to 20 to 30 TeVs, they have seen this. And some of the objects, they have, normally what happens that if electron is taking part to produce this third one, then they should see sudden increase in this one also. When you have seen a peak here, then you should see an increase. But at least 2-3 objects they have seen that there is nothing here, but suddenly they will see a peak here. That is they call orphan flare, because it is not accompanied by anything else, but suddenly they will see that one. And that explanation of orphan flare is extremely difficult using electron to explain that one. Because normally when electron take parts or muon, any charged particles, not protons, so electronic sectors, they take part. So when anything comes here, similarly it should increase, okay? But they have not seen that one. This first thing they have saw in 2002 from the object, well, that is a high energy blazar, that is called 1ES1959 plus 650. So these are the objects, they name this according to the catalog. So this is a Einstein catalog, something like that. So ES corresponds to Einstein survey catalog or something like that. So that is difficult. So like for example, this is extremely difficult to explain if these electrons are taking part. Now also you can ask this question, why only electrons will take part? Because this is producing protons, nuclei and other things. So these particles or hadrons should also take part in this one to explain that. And in fact that is true. But there is another problem with this one is that if you take only protons to explain this one, you need extremely high energy. It is something, it is called in astrophysical sense, it is called super Eddington luminosity. So if you put 5, then to explain that one, you need 100. So then there is no source which can produce that one. So you need extremely high energy in protons, or the flux will be extremely high, which this whole black hole system, this AGN system cannot supply. So that means there is something wrong in our understanding. So one has to go away from that one and think other way, that it is not only proton synchrotron which is producing this, it has to be something else. Okay? Now, let's come to this extragalactic background light. And this is something very difficult. Because of this one, it is very difficult to really extract the information what is going on in the object from where these gamma rays are coming. So what is this extragalactic background light? We know that during the Big Bang, it produces a lot of light, and that light till today is there, but that light has reduced its energy, and it is something like 2.7 degree Kelvin. So this is the core, this cosmic microwave background which is there. Now what happens after the Big Bang? Then star galaxies formation took place, and they produced light because of the nuclear reactions. So all these lights they produced, okay? This light is there, and that light is called cosmic, infrared background, optical, UV, X-rays, gamma rays. So these backgrounds lights are there. It is there like cosmic microwave background, but it is not as abundant as called CMB, but it is still important. So normally what happens is that when any high energy gamma ray signal is coming from somewhere else far away, then they have to face this consequence. So these high energy photons or high energy gamma rays which is coming, let's say this is the high energy gamma rays coming, and this is this extragalactic background light photon is there. So when they interact, according to quantum electrodynamics, what happens is that they will produce an electron-positron pair. So they will produce electron-positron pair, then this high energy gamma rays will lose its energy. Basically, it loses everything. So if the signal is coming far away, you may not be able to see, or it may not reach to Earth or to your detector. So maybe the object is producing extremely high energy gamma rays, but unfortunately it will not reach to the Earth. So this is called the horizon of this high energy gamma rays, that normally this is the factor which comes. So you take exponential to the power -1. So optical depth tau gamma gamma means gamma gamma, this gamma gamma goes to electron positron pair. This is the one which will deplete this flux. So what happens is that, so you have to multiply with this your flux, whatever is coming from the source, by this factor, so that you will see whatever is observed. Okay, so now what happens is that this is a plot where they have shown redshifts versus the cosmic gamma ray horizon, in the sense that when optical depth is 1, that means exponential -1, which is 0.37. So basically what happens is that your flux will be reduced by something like 63%. Okay, so 63% reduction, they have plotted this one, and now you can see, for example, Markarian 421 is a high energy blazar, which is the nearest blazar to our galaxies. So you can see, if it is little more than, let's say it is 20 tera-electron volt photons, which will be reduced by 70% when it is coming from there. So if you increase the energy, then basically you will not see anything. So what it tells is that if your redshift increases, for example, here you see this object, which is optical depth is 1, when the energy is less than even 1 TeV. So you don't expect to see extremely high energy photons from these objects. Okay, so if some objects are like more than redshift 1 or 2 or 3, then it's almost impossible to see these extremely high energy gamma rays. So there is no hope. So in that sense, what it tells is that if you want to see very high redshift object, your Hawk magic detectors or Veritas doesn't work. So it is useless. Only way they will work is that if these objects are comparatively nearby, maybe this object, for example, even from this object, they have not seen any gamma rays which is above 30 tera-electron volt. So although Hawk has a upper limit of 100 tera-electron volt, but nobody has seen any signal beyond 30 tera-electron volt. So this is something very, and this is causing because of this extragalactic background light. So normally what happens, okay, now question is that one has to understand this extragalactic background light properly, so that you can tell about what is the intrinsic flux coming from the object. Now question is that why do you want to study intrinsic flux? Well, the simple answer is, if I don't know intrinsic flux, gamma ray flux, because as I told you, gamma ray flux and neutrinos are related. If I don't know intrinsic flux, then I cannot predict what is the neutrino flux. Okay? Now, coming to the detection of very high energy gamma rays, normally, well, not only high energy gamma rays or high energy cosmic rays or high energy neutrinos, there is no direct way that you will detect them, this object, this particle will come and hit your detector. No, it doesn't happen like that. Normally what happens is that they will come, and by chance they will for example, high energy gamma rays, they will come, then they will interact with the upper atmosphere with particles, and then they will produce these showers, okay? Enormous amount of energy will go into this one, so they will produce millions of particles, and these particles when they come, and then finally low energy photons will come, and this will collect that one, and then they will see from there, they will reconstruct. So these are basically Cherenkov light will come, because charged particle, mostly electrons, muons and all these things, because of this one they will produce. And these charged particles, when they are propagating in air has the properties that it has a refractive index extremely little above 1. So that little above 1 will cause the Cherenkov light emission from these charged particles, and then that charged particle will produce these photons, and that photons will be collected. So these are detectors or antennas, you can tell. So they will collect these photons to tell about this one. Now, so we have to detect this extremely high energy gamma rays. We have many detectors on Earth. One is called HEGRA, high energy gamma ray radio ray astronomy. Then MAGIC, HEGRA has updated to MAGIC, which is in La Palma, Canary Island, which has a threshold of 30 giga electron volt to 100 tera electron volt. HES is in Africa, which has also a similar upper limit. Veritas is in USA. It has 50 GeV to 50 TeV range. And HAWK is in Mexico, which has the highest energy upper limit. And also this detector is completely different from this rest. These are air Cherenkov detectors, and this is water Cherenkov detectors. It has a duty cycle is, I think, 100%, but these are duty cycle, only they will work in the night, that too moonless night. If there is moon, this doesn't work, okay? So to show you some of these pictures, MAGIC detectors, these are two detectors look like this one. Then HES telescopes, so just for the comparison, we have put this one, how big this is. Then Veritas is also quite big. Then HAWK. So these are the detectors which detects very high energy gamma rays. Okay, now, so to explain this, this flaring or few hundred GeVs to TeV gamma rays, it is not easy to use electron, I mean the same electronic model. Well, in fact, it is almost impossible to explain that one. So many people, they try to explain this TeV emission using both electrons and protons, but again, there is a difficulty. So since last 4 or 5 years, or I think little more than that, myself and with my collaborators and students have developed a model that is called the photohadronic model. Normally what happens is that the idea of this one is that when a high energy proton comes during the flaring, mostly during the flaring when you produce high energy gamma rays, these protons comes within the jet, then it interacts with the background photons and produce a delta resonance. I will show you the reaction, the next one. Then it can produce both charged pion, mostly pi plus, not pi minus, unless it is a multi-pion productions, and then pi zero. So pi plus will decay to muon, and then subsequently it will decay to neutrinos and antineutrinos. And pi zero or neutral pion will decay to gamma rays. Now these gamma rays, when they are coming, when there is a extragalactic background light, they will produce E plus E minus pair and degrade in energy, so that you will not able to see these gamma rays, but you will see low energy, or you may not able to see, because on the way these again, because they are still high, so they will produce a lot of particles, and finally you may not be able to see high energy gamma rays, but you will see maybe radio. If you are lucky, maybe you will see mega electron volt to some giga electron volt particles. Okay, so these particles in the jet they will be accelerated through different mechanisms. One is most favorable, one is the Fermi acceleration mechanism, because in that jets, this is not continuous flow. There will be flow like intermittent flow. One wave goes, after a few seconds another wave comes. So they have different Lorentz factors, they have different speed. Because of that, one particle will, it is like oscillation bouncing back and forth, and then they will gain energy or lose energy. The particles which lose energy, we don't talk about that one. The particle which gains energy, then we talk about that one, because that is the one which will produce interesting effect. Okay, so this is the mechanism through which it will produce. Well, there are other mechanisms also it will produce, but this is the one which has a cross section very high, because it is a resonance, delta plus is a resonance. So this is the one which is important, very important. We found that this is the most important reaction which contributes. I will show you later on some of our results. Then, okay, so some of our results. We said that this is a Markarian 501. It had a flaring in May 2009. Well, there are a lot of flarings, but I cannot put all of them here. Just to show you, is 2009 there was a flaring, and these red points are flaring. And using this photohadronic model, we explained this one. This is our curve, this black curve. Then 1 ES 1011 plus 496, it had a flaring in March 2014. And these are the red points are the result. And to let you know this dots lines, this was first written in 2006, a Nature paper claiming that these objects has a hard emission. But we showed that in 2017, we showed that no, this is not a hard emission. This is a usual object and it emits like any other objects, and we showed that it clearly follows this. So either you can tell red curve or this black curve, because it depends again on the extragalactic background light model. So if you take that one, you can explain both. With both, you can explain very well. Then this is another object which was flaring in 2004. Again, this is our result. Then Markarian 421, which has an eruption or flaring in February 2010. Again, we explained this extremely well. I think this is the only calculation which explains very well the result. Not even the experimental people, they explain that one quite well. Then this is the one which was very interesting. In 2002, they saw a orphan flaring. This is the orphan flaring, and there was absolutely nothing going on here. So we also explained this one using this model very well, you can see. Now, this another object which is very interesting, again, also we explained that. Well, we have explained, now we are writing a paper, we have explained so far 47 objects quite well with this one. So this is something very interesting. Okay, now let's come to the neutrino astronomy. Well, probably most of you know that when, let's say this is the object which is producing these high energy particles, whether it is proton, neutrinos or gamma rays, but protons normally what happens that when high energy protons, they will be deflected in the magnetic field, and so maybe this proton will reach somewhere else here, so you will lose directionality of that one. Or if it is really high energy protons, this will never reach, because this proton will interact with cosmic microwave background and produce other particles. So then you will not get any information about these protons. Now, you take gamma rays. The gamma rays, if they are low energy, probably they will come. But if they are high energy again, these gamma rays are coming, and on the way, this extragalactic background light with that one, they will produce E plus E minus pair, then they will lose all the information, so you don't get. So they have to be comparatively low energy in the sense that, well, I mean, it depends on the distance, not very far away and not extremely energetic, then you will not get any information. So they will come maybe around 30 to 40 tera electron volt gamma rays will come. But again, that is again a difficult thing. But if you are producing neutrinos, there is nothing it can stop them. Well, there are background neutrinos, they can stop probably, but that is extremely small. But if you are producing these neutrinos, they can come directly to your detectors, and if you are lucky, you can detect them. So that is precisely the idea that neutrino detectors are operating to detect these neutrinos. Another important thing is that suppose you get a proton signal from here, gamma ray signal from here, and neutrino signal from that same place. Then that is something very interesting, that this object is really the powerful object which is producing all these three. Okay? So that is precisely what now most of these experiments are doing. Now, to detect neutrinos, well, I am not talking about low energy neutrinos. These are neutrinos above 20 to 30 tera electron volt neutrinos. So this is the detector in south pole which detects. This is, you can see, around 1.5 kilometers underground, and this is the you can tell this is the detectors. And to compare this, the Eiffel Tower, you can see so small Eiffel Tower compared to this one. And so this detector looks like this. These are steel strings hanging, and these are the optical modules which are hanging in this one. And any light signal comes, they will catch that one. So these are the specification of this neutrino telescope: 86 strings, 160 ice-top tanks, and these are all, numbers you can see. Okay. How do they detect? Okay, so normally the IceCube is designed to detect mostly, it is interesting to detect neon neutrinos. Well, it will detect electron and tau neutrino, but it cannot differentiate between electron and tau neutrinos, but it can differentiate between neon neutrino and rest of the active neutrinos. So this is not just a sketch. This is a real one. What they have generated. Only thing is they have put different colors. So a neutrino is coming from these directions. So the red one is the first where it hits, and the other colors are second. So like for example, here you can see, well, this is a shower event. I will tell what is shower and what is track event. And it produces, and then this, because light goes out, then it will trigger different modules. On the other hand, here you see the particle is coming from this direction. This is the arrow. So it trigger first here, and it is going in this way. And this is a long, it is almost around 1 kilometer track. So this is the one. From there, they will see that normally what happens is that neon can travel kilometers depending on its energy before it decays, and they can see, compare the type of track they have, whether it is a bunch like this or a long strip like this, and from there they will see whether it is a neon type or rest type. For example, physics wise what happens is that if you have an extremely high energy neutrino coming, it enters to the earth and it interacts with the rocks nearby or ice nearby in the detectors. Then if it is, we know that neutrino can have two types of interaction. One is charge current interactions, another is neutral current interactions. In the charge current interactions, it will produce a corresponding leptons. Neon neutrino will produce a neon, electron neutrino will produce a electron, or tau neutrino will produce a tau. So now what happens is that if it is charge current interaction, then it will produce a neon, and this neon can travel long distance, and first of all, it is a charged particle, and second thing is that ice has a refractive index 1.31. So in this ice, when this charged particle propagates, it will produce a Cherenkov light. So that Cherenkov light, it is a cone, it will go very straight because neon will not lose that much energy. It will go very straight, and if you see transversal one, it will show you it is like a circle. On the other hand, neon and electron and tau neutrinos, they will be absorbed very quickly in the medium, and they will be zigzag. Because of this zigzag, they will produce a diffuse circuit. From there they will see this. So these are the two basically important ingredients in IceCube detectors to differentiate between the neon neutrino and tau neutrino. Sorry, neon neutrino and electron and tau neutrino. Now, so far IceCube has seen, well, it was when they produced ICRC 2017, because after that they have not reported anything. So 103 events, 6 years, 103 events, with 60 events above 60 tera electron volt. You can see that this is the energy and this is their declination. So most of these are something around 300, less than 400 tera electron volt neutrinos they have seen. They have seen 3 events which are PeV neutrinos. PeV means 1 PeV is 10 to the power 15 electron volt. Okay. So these are 3 events. These events they had seen, well, I mean, they tell, this is something very interesting, that before this event came, you can see there is a gap between 400 to 1 PeV. So they were thinking that maybe there is a real gap depending on the physics, but we don't know really whether there is a gap or not, which has to be known after taking much more data. Okay, so now from the first analysis they saw 35 events, and from there they saw that really, well, this is one of our paper which we published. So we saw that whether some of these neutrinos, because from there you can see really from which direction neutrino is coming. So the coordinates you can really specify. But that's the problem, this one. If it is an electron or tau neutrino type, the error in this cone is something like angular error is something like 10 to 15 degrees, so it is very difficult. But if it is a neon type neutrino, it is less than 1 degree. So that's why if it is a neon type of neutrino, it is extremely easy, or rather it is easy to tell from which direction it is coming. So we try to reconstruct, telling that suppose high energy blazars are important candidates, they produce this because they are producing tera electron volt gamma rays. So they are the objects which are responsible for these neutrinos, and then we try to reconstruct and see whether they are really there or not. For example, this is one of the most important object, Centaurus A. From that direction they got a neutrino of 2 PeVs, which is the highest one, and we saw that that is exactly within this Centaurus A region. Then there are other things. So then it shows that really these high energy blazars are possible candidates to produce these neutrinos. So this is basically the results. ¿Cuánto tiempo tengo?
We have like 5 minutes.
Okay, so these are the objects, and we sort calculated what will be the neutrino flux. But unfortunately, statistics is so poor, you cannot tell. With around that time it was 37, I think 37 events. So with that one, it is very difficult to tell whether these high energy blazars are possible candidates or not. But many of them were within this error bar, these events. Then observation of high energy neutrino, this is something very spectacular in 2017. On 22nd of September 2017, IceCube neutrino telescope in South Pole detected a track-like neutrino event. Track means it is a neon type of neutrinos, which has less than 1 degree error in the direction from where it is coming. So very accurately they can tell from which direction neutrino is coming. So they detected a neutrino of around 300 tera electron volt from a direction, that is something very important. From a direction, well, from the direction where it is coming, that time they saw that in that direction there was a high energy blazar, or there was a blazar named TXS056 plus 056, which is at a redshift of 0.33, was flaring. And they saw So all these high energy telescopes, low energy telescopes, optical telescope, everything, I think around 30 telescopes of different energy, they zoomed into that directions, and most of them, they saw that something is happening there. Either in the low energy limit, the flux is going on, in the intermediate energy limit, the flux is going, and in high energy limit, flux is going, and they saw also neutrino from that directions. Then they saw that the most important satellite detectors like Fermi-LAT, which observe in GeV energy range, this saw a really huge change in the flux or increase in the flux. Then after that, once it observed, after that, this magic telescope observed high energy gamma rays from that directions between 95 tera electron volts to 366 tera electron volt. They saw the gamma rays from that directions. So then it shows that something is going on in that directions. So it is not only neutrino which they saw optical, radio, infrared, then gamma rays, GeVs, then they saw this up to 400 GeVs, gamma rays by magic telescope. Then they saw that these blazars are really important candidates for production of high energy neutrinos. Now question is that if you produce high energy neutrinos and high energy gamma rays, then you must produce high energy cosmic rays. There is no other way, because if you don't have high energy cosmic rays, these particles, particularly neutrino, cannot be produced, because it is a pure hadronic process unless you are talking about some physics which is beyond the standard model physics. Okay? Now, so to summarize this one, observation of very high energy gamma rays and neutrinos from Blazar shows that this extreme condition in these objects can back really very high energy gamma rays and neutrinos. So that's why it is a back carry for high energy gamma rays and neutrinos. Of course, high energy cosmic rays are the primaries from which both gamma rays and neutrinos are produced. So blazars are sources of high energy gamma rays, neutrinos, and cosmic rays. But with this very less number of events, it is almost impossible to tell that whether really these are the objects or not. But one has to really do more observation, ample data, and required to reconfirm these claims. Okay? With this, I thank you very much. Well, maybe I should tell about this one, because my student asked why you have put this one. So this is something interesting. This is a tree in Madagascar, baobab. This tree, they tell that this can live up to 3,000 years. And carbon dating also, they have seen a tree which recently, 2011, it died. It was 2,400 years. So National Geography, and this is a street around 260 meters. So there are a lot of trees of this type are there, and from there they took the picture of the galaxy. So these trees are as ancient as the human civilization, so they have taken this one. So I thought that maybe I will put this here. Thank you.
Bueno, pues muchas gracias. Y si alguno de ustedes tiene una pregunta, algún comentario que hacer, esperen al micrófono porque estamos en YouTube.
I wanted to know what are the free parameters of your delta model.
In our delta model or photohadronic model, only free parameters so far only is the spectral index. With that one you can, well, of course you have to use the leptonic model, the low energy one, because high energy protons will come, hit the background photon, so that background photon information we have to know. For that, whatever low energy information is there, from the leptonic model we take that one. But from there onwards, we need only spectral index of the proton. Not even the normalization constant, because normalization constant can be automatically seen. So there is only one parameter.
Yes, very nice observation. Now, I'm wondering, we still do not have any idea of the production of this very high energy neutrinos or gammas, no?
TeV neutrinos to produce in this model, you need a proton energy of around 6 PeVs. But now question is that whether these objects can produce 6 PeV neutrinos or not. We don't know. But from the parameters and all these things, they tell that it can produce up to 10 to the power 18 electron volt particles, cosmic rays. So in that sense, we believe that it produces.
But actually, so this comes out of a black hole.
No, well, I mean,
No.
nothing will come out from the black hole, but it is normally what happens is that, maybe I should, here it is better. Okay, so normally you can tell that this is the event horizon. If you go beyond this, nothing comes out. But your jet, what it produces somewhere else here. It's outside. So outside the event horizon, well, otherwise it cannot come.
Yeah.
Yes, so from there these particles are when the matter is falling into this one, then jets comes in this way, another jet will be another way, and from there, these particles in this jet, when they are propagating in the magnetic field in extreme conditions, they will be accelerated.
¿Otra pregunta? Bueno, pues...
Cualquier pregunta.
Sí. Bueno, pues muchas gracias, doctor Sarira Sahu. Gracias a todos ustedes por venir. Y pues los esperamos para nuestros siguientes coloquios. Acuérdense que en Facebook y en Twitter los estamos anunciando todo el tiempo. El 29 tenemos la celebración de los 100 años del eclipse de 1919, el 29 de mayo. Tendremos 2 charlas y una mesa redonda para discutir sobre nuestro tortuoso 100 años de un tortuoso vaivén entre teoría y observación, justamente este tipo de problemas. Nuestras teorías al límite cuando observamos el universo. Muchas gracias. Gracias, doctor.
Gracias.